Hello everyone. Today we are going to study one of the transforms known as Z transform. This Z transform is the generalization of discrete time Fourier transform. Use of Z transform is very important in the analysis of linear time invariant systems. Many systems occurring in statistical studies and in engineering fields are discrete in nature. These discrete systems, they give rise difference equations which are solved and analyzed using techniques of Z transform. Many digital systems including resonators, different filters and oscillators uses Z transform for their analysis. Z transform plays same role in discrete systems as Laplace transform in continuous systems. So let us go to study such transform which is known as Z transform. In this lecture, we are going to see some prerequisites for this Z transform. In the prerequisites, we are going to see what is meant by the sequence, causal sequence and properties of the sequence. So first of all, we will define sequence. Sequence is an ordered set of real or complex numbers which is denoted as in curly braces f suffix n or in curly braces f of n. Let us see the representation of the sequence. There are total two ways. First way is listing all elements. Consider the example. Example, the sequence f of n is equal to whose elements are 2, 5, minus 1, 3, 8, 7. Below this minus 1, this arrow is given which gives us the position of this minus 1 in this sequence and it is the position corresponding to n is equal to 0. Using which we can easily obtain position of the remaining elements of the sequence in the sequence. That is, this 3 is the element corresponding to n is equal to 1, 8 which is corresponding to n equal to 2, 7 corresponding to n equal to 3. Similarly, on the left hand side of this arrow, this 5 will be the element corresponding to n equal to minus 1 and this 2 will be the element corresponding to n equal to minus 2. That is, we will be getting f of minus 2 equal to 2, f of minus 1 equal to 5, f of 0 equal to minus 1, f of 1 equal to 3, f of 2 equal to 8, f of 3 equal to 7. So we got this listing because of the position of this arrow. Now consider the second example. F of n is equal to 2, 5, minus 1, 3, 8, 7. If we observe the first example, elements of both the sequences in the first example and the second example, they are same. But here, what is the difference? In the second sequence, arrow is given below the entry element 5 and therefore this 5 will be the entry corresponding to n is equal to 0. To the left 2 is there which is the entry corresponding to n is equal to minus 1. So see, if we compare with the previous sequence, then here position of all the elements got changed and therefore both the sequences, they are different because we know that sequence is an ordered set. So order of the element is very important. So for this sequence now, f of minus 1 equal to 2, f of 0 equal to 5, f of 1 equal to minus 1, f of 2 equal to 3, f of 3 equal to 8, f of 4 equal to 7. And if we see the previous sequence, position of the same elements is different in that sequence. We consider one more example. F of n is equal to whose elements are minus 2, 4, minus 6, 1, minus 8, 7. Here arrow is not given below any of the elements. Hence, the left hand term, that is minus 2, will be treated as 0th element. That is, the element corresponding to n is equal to 0 and therefore we will be getting f of 0 equal to minus 2, f of 1 equal to 4, f of 2 equal to minus 6, f of 3 equal to 1, f of 4 equal to minus 8, f of 5 equal to 7. So for in case of this third example, this is very important to keep in mind how to get the zeroth entry whenever arrow is not given below any of the entry. Okay, so the left hand entry will be treated as zeroth entry. So this is the first way of representing the sequence, that is listing of all elements. Okay, here we have considered only finite sequences in which we have listed all the elements. Now we will go to the second way of representing the sequence. Second way is to define general term as a function of position, that is n. To understand this, consider the example f of n is equal to 1 upon 2 raised to n. So see here we have defined a function in terms of the position, that is n, where this n belongs to set of integers. Now put the values of n one by one and get the elements of this sequence. So the sequence will be like this, dot dot dot. This one is the entry corresponding to n is equal to minus 2, which is 1 upon 2 raised to minus 2. Put n is equal to minus 1 here. That will give us 1 upon 2 raised to minus 1. So this one is the entry corresponding to n equal to minus 2. This one is the entry corresponding to n equal to minus 1. If we put n equal to 0, it will give us 1 upon 2 raised to 0. That is 1 upon 1 equal to 1. Put n equal to 1, that will give us 1 upon 2 raised to 1. N equal to 2 will give us 1 upon 2 square and so on. So this 1 is the entry corresponding to n is equal to 0, which is the zeroth element. So same sequence also can be written as so on. F of minus 2 equal to 1 upon 2 raised to minus 2, f of minus 1 equal to 1 upon 2 raised to minus 1, f of 0 equal to 1, f of 1 equal to 1 upon 2 raised to 1, f of 2 equal to 1 upon 2 square and so on. Hence f of n in general can be written like this. Now consider the next example. F of n is equal to 3 raised to n, where n takes the values from minus 2 to 3, which are the finite values. So put n equal to minus 2, minus 1, 0, 1, 2, 3. That will give us elements of the sequence as 3 raised to minus 2, 3 raised to minus 1, 1, 3, 3 square, 3 cube respectively. Here 1 is the element corresponding to n is equal to 0. That is, it is the zeroth element. Same can be written as f of minus 2, f of minus 1, f of 0, f of 1, f of 2, f of 3. So these are the two ways to represent the sequence. First one is listing all elements and second one is defining general term of the sequence in terms of position, that is n. Now we will define next causal sequence. So let us see what is meant by causal sequence. Any sequence whose terms corresponding to n negative are all 0. That is, consider the example. If we consider the sequence whose entries are like this, then 1, 1, 1 and so on. So all remaining they are 1 only. All the elements they are 1 only. Now below the first non-zero entry, arrow is indicated below that first non-zero entry. So this is the zeroth entry. All the entries to the left of zeroth entry, they are 0. That is for n negative, all the entries they are 0. So such sequence is called as causal sequence. And they are very important in case of the linear time invariant systems. Second, consider this example 2, 5, minus 2, 1, 3. So this is the finite sequence, but sometimes we need to make it an infinite sequence. Then in that case we will add zeros on both the sides of this sequence like this. So this will becomes an infinite sequence. So this is also a example of a causal sequence. Now we will go to see some properties of sequences. Consider the operations on sequences. For that, we will consider let f of n and g of n be two sequences. So this f of n and g of n are the general terms for the respective sequences. First operation is addition. If we add the two sequences, sequence f of n and sequence g of n, then they results in the new sequence whose general term is f of n plus g of n. For example, these are the two sequences, sequence 1 upon 2 raised to n and sequence 3 raised to n. Then their addition is the new sequence whose general term is 1 upon 2 raised to n plus 3 raised to n. Next is the scaling operation, that is, to the given sequence f of n, if we multiply by any scalar k, then that sequence will be k into f of n, means we have to multiply each of the element of the sequence f of n by that scalar. The meaning of k into f of n is we have to multiply each of the element of the sequence f of n by the scalar k. For example, if we consider the sequence 1 upon 2 raised to n, and if we multiply it by the scalar k equal to 2, then it gives us 2 upon 2 raised to n, and simplifying it we will be getting 1 upon 2 raised to n minus 1. Means here we have multiplied each of the element of this sequence 1 upon 2 raised to n by 2. So that is the scaling operation or the property. Next, third is linearity. This linearity is the combination of addition and scaling. If we consider the sequence whose general term is alpha into f of n plus beta into g of n, then this can be written as the sum of two sequences like this, that is alpha into f of n plus beta into g of n, where these alpha and beta, they are scalars. So this is the linearity property, and these are few operations on the sequences or properties of the sequences. I hope you understood this. Thanks for watching this video.